All right, today we are diving deep into a really fascinating paper by S.B. Thorway. It tackles a question that gets at the very nature of empty space itself. The paper puts forward a new idea, dynamic vacuum field theory, and it uses this really strange, really cool process to test it. The idea that light can actually turn into gravity. So yeah, let's get right into it.
I mean, it sounds like something straight out of science fiction, right? Can a photon, a little particle of light, actually transform into a graviton, the hypothetical particle of gravity? Well, this is the big, provocative question we're digging into today. And believe it or not, according to physics, the answer is kind of yes.
But look, this isn't just some theoretical what if. The mechanism for this transformation actually has a name. It's called the Gertsenshtein effect, and it's totally grounded in established physics. So first, we're going to look at how this is even possible inside the framework of general relativity before we see how this new theory adds a really interesting twist.
Okay, so let's start with the baseline, our current best understanding of gravity, Einstein's general relativity. Now, with NGR, the Gertsenshtein effect is a predicted thing. It's supposed to happen, even if it's incredibly rare. Let's break down what's actually going on here.
So what's the secret ingredient? What kicks off this transformation? It's a magnetic field. The Gertsenshtein effect basically says that if you shoot a beam of light through a really powerful magnetic field, that field can act as a catalyst and actually mediate a conversion, turning some of that light into gravitational waves.
So how on earth does this work? Well, conceptually, think of it like this. A photon flies into a magnetic field. The field then does what the paper calls spin bookkeeping. Basically, it handles the momentum transfer that lets a spin 1 photon flip into a spin 2 graviton state. Now, this isn't an instant switch. It's more of an oscillation, a mixing process, kind of like how neutrinos oscillate between their different flavors as they travel. And there's just a tiny, tiny chance that when the particle pops out the other side of the field, it will have locked into that new state and emerged as a graviton.
And when I say tiny, I mean it. The paper actually calculates the probability for a single photon traveling 1 AU, that's the distance from the Earth to the Sun, through our own solar system's magnetic field. The chance of it converting is about 1.5 times 10 to the minus 32. I mean, that is a number so small it's hard to even wrap your head around. So here's the bottom line for standard GR. The Gertsenshtein effect is a real, predicted phenomenon. The theory says it can happen, but the probability is so ridiculously low that, for all practical purposes, it's totally unobservable. It's basically a theoretical footnote. But what if our theory of the vacuum is incomplete?
And this is where the paper introduces a huge paradigm shift, dynamic vacuum field theory, or DVFT for short. It challenges our most basic assumption about space, the idea that the vacuum is just empty. DVFT says, no, the vacuum is a physical, active medium. The core difference here is pretty profound. You know, in GR, we think of the vacuum as just the empty stage where all the physics plays out. But in DVFT, the vacuum is one of the actors. It's a physical medium with its own properties that can actually change depending on the environment. And that, in turn, can affect how things travel through it. Okay, the paper formally defines this vacuum as a complex scalar field. Now, you don't have to worry about the math here, but the key idea is wild. It suggests that properties like inertia aren't actually fundamental constants, but are instead encoded in the state of the vacuum itself. That's a really deep shift in thinking. Now, for any new theory to even get off the ground, it has to match what we already see. And DVFT is designed to do exactly that. In high-gravity, high-acceleration environments like our solar system, its equations basically reduce to general relativity. Everything looks the same. But in the weak, deep field environments between stars, that's where its unique, nonlinear properties are supposed to pop out. This two-regime structure is absolutely key to testing it. So how does this new vacuum model change our light-to-gravity conversion? Well, by treating the vacuum as a medium, DVFT implies that it can actually affect the speed of light. And this introduces a brand new problem for the Gertsenshtein effect, a coherence problem. Think about that whole oscillatory conversion thing. For that effect to build up over really long distances, the photon and the graviton waves have to stay perfectly in sync. They have to be in phase. But if DVFT is right, and the vacuum has a refractive index, like a piece of glass, it could slightly slow down the light while leaving the speed of gravity alone. The two waves would slowly drift out of phase, and that would kill the conversion process. Let's look at what's going on under the hood here. In GR, the wave vectors for the graviton and the photon are essentially identical. They travel in perfect lockstep at the speed of light, c. No problem.
But in DVFT, see that NDVFT term, the photon's wave vector gets modified by this refractive index of the dynamic vacuum. If that number isn't exactly 1, you get a phase mismatch. Simple as that. The direct result of this is something called the coherence length. You can think of it as a physical speed limit on the conversion process. Once the waves travel this far, they get so out of sync that the conversion just stops building up. This introduces a hard limit on the conversion, and that limit is a totally unique prediction of DVFT.
Okay, so we have two different theories making two different predictions. And for physicists, that's fantastic news, right? Because it means we can actually design a test. These differences between GR and DVFT lead to brand new and potentially observable signatures out in the cosmos.
And this brings us right to the core prediction of the paper. Here, in our solar system, a strong field environment, DVFT acts just like GR. The conversion chance is practically 0 because the magnetic field is just too weak and the path is too short. But out in the deep field environment of the Milky Way, the new physics kicks in. The coherence length becomes the new limiting factor, and this is the key part. That length depends on the frequency of the light. So listen, this is the most important takeaway. The paper is not predicting we'll see more light-to-gravity conversion. In fact, for most frequencies, it might even be less. The real smoking gun for DVFT would be a different pattern of conversion, one that's completely dependent on the frequency of the light that we're looking at.
And this gives us a brand new, really clever test for fundamental physics. Instead of just looking for any old photon to graviton conversion, astrophysicists could start looking for specific frequency patterns across huge cosmic distances. You'd be looking for what the paper calls coherence windows, specific frequencies of light that seem to convert, while others don't. Finding a pattern like that would be incredibly powerful evidence for a dynamic vacuum. And, well, not finding it would help constrain the theory.
And this leaves us with a final, really profound thought. What this paper suggests is that some of the deepest secrets of our universe might not be hidden away in giant particle colliders, but in the subtle, hidden structure of what we've always just assumed was empty space. Could the very fabric of the cosmos hold the key to the next generation of physics? It's an incredible thing to think about. Thanks for joining us.